Hello, everyone. Welcome to Intelligent JVM monitoring session. My name is Yagmur, and I work at Oracle in a JVM sustaining engineering team. Today, I'm going to talk about how we can combine JDK Flight Recorder with AI. This talk was prepared in collaboration with my colleague Joachim. Together, we explored what we can do. So let's just dive into it. Imagine you have a monitoring dashboard of your application that looks like this. And one day you see all these alerts and performance looks terrible and you get a lot of angry customer messages. This is exactly what happened to a business called Galaxy Cafe. What does this Galaxy Cafe do? It's a cafe somewhere out there in the universe where aliens hang out and order coffee. But as you can imagine, it might not be very practical to travel across galaxies to just order a cup of coffee. That's why Galaxy Cafe also supports online ordering and shipping. And their ordering system is designed as an above-the-cloud application. And it is built using microservices architecture, and everything is running on Java. So the monitoring dashboard we just saw earlier is from last year's Interplanetary Galactic Coffee Day. And every year on this day, Galaxy Cafe offers some special discounts, and they get a lot of orders than usual. And after having the performance issues last time, this year they want to be a bit more precautious, so they want to monitor their application. And today we will help them design an intelligent monitoring system to make sure the same problem doesn't happen again. Okay, today's agenda. First, we'll look at their microservice architecture, and then we're going to discuss how we can help them. And then we're going to talk about three main concepts. These are JDK Flight Recorder, Java Management Extension, and Artificial Intelligence. And then we're going to wrap up with a summary. Okay, first, let's look at their system. An alien customer places an order, and in Galaxy Cafe, order service receives it. And then this service validates the customer registration with customer service, and it checks whether the ordered product is available or not with product catalog service. And if everything is okay, then barista service prepares the order and then ships to the customer. These microservices are implemented in a containerized cloud environment, and each of them runs on JVM. Everything is pretty straightforward so far. What about monitoring? How can we help our alien friends about this? Well, of course, we will do this with JFR, and JFR is the low overhead monitoring feature of the JDK that emits events from the JDK, JVM, and the application itself. And one common way to use is with start flight recording flag. And this directly starts the recording when the JVM starts. So now, if we notice a disturbance in the performance, for instance, maybe in order service, an engineer can log into that machine, run a JFR dump and download the recording, open it in Java Mission Control, and analyze it to understand what went wrong. However, this might be quite cumbersome because the problem might not be in the order service. It might be in the customer service or in product service or somewhere else. And in that case, we need the recordings from those services as well. And by the time we discover that the issue in the order service is not caused by the order service, but maybe it's in another service, then maybe the actual problem might already be gone. So instead of this approach, we want to do something different. We want to enable the JFR on each microservice, but instead of storing them locally, we want to stream them into a centralized monitoring system. And on the monitoring service side, instead of engineers analyzing all the events manually, monitoring them manually, we want AI to do this instead of us. And ideally, to make the system even more automated, if we detect something, then we want to take some actions to heal these performance problems in runtime through JMX. Okay, first, how are we going to capture the JFR events? One way is to use the start flight recording flag that we already saw, which starts the recording when the JVM starts. Another option is to start the recording later while the application has been already running by using the jcmd command and applications PID. But in our case, we want to stream the captured events to our monitoring system. Therefore, we will capture them programmatically by using the JFR API. So let's define a class called JFR streamer with a method called capture and send. In this method, we're going to use a server connection to our monitoring system, let's say AI server, and that way we can forward the events that we captured. To create a recording stream, we first need a JFR configuration. The JDK is shipped with two standard configurations. These are default and profile. And if you are curious, you can go ahead and see this path under OpenJDK. The default configuration is designed to be always on with a very low overhead, less than 1%. And the profile configuration enables some more events, so it might introduce slightly more overhead, but it is still suitable for profiling applications. So once we have the configuration, we create the recording stream, and this stream allows us to register an event handler. This is going to be triggered every time we receive a JFR events. And that way, within the event handler, we can process the events and send them to the monitoring service. And our handle event just takes the recorded event, converts it to string, and then posts to an endpoint that monitoring system can access. So this might be a bit problematic in our case, because if we send every event, then we might create a traffic in our network. Even though the default configuration is designed to be always on, still it enables around 90 different events. So in our case, with such event handler, it might not be the perfect option. So therefore, we can load the configuration from a configuration file, and we can customize which events are enabled for our use case. And to do that, we can add a custom JFR config file like custom ai.jfc on each microservices, or we can have a centralized custom JFR config on only monitoring service side. And with this get config method that we define, we can expose the configuration to a configuration endpoint, and each microservice can fetch during startup. And in the next section, we're going to use Java Agent to make this possible. And the response can be used in configuration.create, and then we can create our recording stream. To call the events handler, we need to iterate through our custom configuration file, and the entries in the configuration follows this format on the left. It is jdk.eventName, hash, the field of the event, and the value. So here we iterate the events in the config file, and every time we receive every time JVM emits an event with enabled field is true, then we're gonna call our events handler. And finally, we run our recording as start async. And this starts the JFR recording stream in the background. So events are going to be handled in the background without blocking the application. Okay, now we have to set up this starting the JFR recording and streaming on each microservice. And to run this for each microservice, automatically at the startup, we decided to use Java agents. This makes it easier to enable the recordings for all microservices. To use the Java agent, we just need to use the -Java agent flag while we are starting our application, and followed with a jar file of this agent. And to build this jar file, we need two things. The first thing is a premain method. We need to implement this premain method, and it is called before the JVM runs the application's main methods. We also need a manifest file where we specify the class that contains the premain methods, which is agents in this case. And the agent jar includes this as the premain class attributes in the manifest. Here we can also add some arguments to the agent. For example, we can specify a base URL of the monitoring service that we're gonna send the captured JFR events. We can also specify the microservice name so that the monitoring system can know from which microservice that we are receiving the events from. And now that we have the agent in place, we can connect to our monitoring server with the server connection, and we can use our JFR streamer class that we just created and call the capture and send methods. And here it is also worth noting that if we do something that takes time in premain, or if something fails in premain, then the application's main method is going to be delayed. We don't want that. So it could be good practice if we start a new thread in the premain to allow the application startup normally. So far, we started JFR recording with Java agent in each microservices, and we streamed them to the monitoring service. And now we're going to talk a bit about JMX and how we can control the microservices. JMX, Java Management Extension, is a long-standing feature of the JDK introduced in Java 5 back in 2004. So it's definitely not a new trend, but it is very powerful and useful feature. It's an extension that allows you to monitor applications and also dynamically configure and control. And many third-party tools and application servers like WebLogic, Tomcat, they use JMX. We can enable JMX by using the -dcom sun management JMX remote flags. We can provide the port, and if we are doing like local testing or development, we can also disable the SSL and the authentication. So the fundamental concept in JMX API are the managed beans or mbeans. There are default mbeans already registered in the mbeans server, but we can also create our custom mbeans. And a JMX client interacts with the mbeans that are registered in the mbeans server. An mbean exposes two main things. These are attributes and operations. Attributes are the getters and setters that allows us to read and write some configuration. And operations are the methods that perform some kind of action or task. So here we're gonna be talking about two different types of mbeans. One of them is standard mbean, and the standard mbean is simply a Java interface. Its getters and setters are the attributes, they define the attributes, and the other methods are the operations. Then the MBean server uses reflection to expose these attributes and operations through JMX. And the next MBean is dynamic MBean. With dynamic MBean, we create a class that implements dynamic MBean directly. This class provides methods like get attributes, set attributes, invoke, get MBean info. Here we can define both the metadata and the behavior programmatically, and we are a bit more flexible while defining the metadata with dynamic MBeans. Okay, now that we have the theory, let's see JMX in practice on our microservices. Well, first, let's remember how our microservices look like. Briefly, we receive the order to our order service, and then it validates the customer with customer service, and then it fetches the products from the product catalog service. What can we control here to prevent some problems? This is a difficult question. But for instance, maybe on the product catalog service side, we might have a search cache, and we might want to clear this time to time to prevent any potential memory pressure. And the second thing could be how we fetch the products from order service side, because maybe on usual days we can fetch a single product at a time because it is faster, but on busy days it might be a good idea to fetch batches of products. And once we have the control over these things, for instance, on the order service side, we can have something like this. While we are fetching the products, we can check just whether the batch is enabled or not. If it is not enabled, we can just fetch the products in single mode. So now we will do this with JMX. So first, let's see how we create and register MBeans. So now we are in the microservice. Let's just continue with our example, enabling batches. And we just create a class, batch config, that implements dynamic MBean. And we first get the platform MBean server. And the platform MBean server is the built-in JMX server that comes with the JVM. So it runs in the same JVM as our microservice is running. Then we create an object name for this MBean. And the first part is the name of the package. And then we provide a key value pair just to distinguish this particular MBean, because we said that there are other MBeans registered in the same MBean server. And let's just say that this MBean's type is self-healing to show that this MBean can be used in our self-healing setup. And we provide the name of the service and the name of the MBean. And we simply register this MBean to MBean server. And now we have an active MBean at port 9011, for instance. Operations and attributes. So we said operations are the methods that we take some tasks or do some actions. And to do that, we should override a method called invoke so that we can invoke it remotely. And we mentioned that we can maybe clear the cache. So whenever this invoke receives the corresponding action name, it's just going to execute clear cache, for instance. And attributes, we said that they are readable, writable properties exposed through JMX. So we can implement batch configuration with get attribute by overriding get attribute and set attribute. So far, we created the MBean and registered to the MBean server. Now we are in the monitoring service side, and this system doesn't have any idea what kind of microservices out there or what kind of MBeans. So that's why we just named our class as MBean Discovery Service. We're going to discover. And to do that, we create a JMX connector through a port, let's say 9011, by using the JMX service URL. And this way we can just establish a connection to the remote ambient server. And this server connection has a method called query names. With that, we can get all the ambients, list of all the ambients registered to that ambient server. But as we said, we are not interested in all of them. So we are gonna filter for the types that have self-healing that we already described before. Okay, now let's talk about some AI parts of this system. And here I would like to mention that like our first approach was a bit fundamental. We simply used just one single LLM to do all the tasks for us. But then we realized that it might be more efficient to divide the responsibilities into several LLMs. And that's why we moved our approach to AI agentic approach. So today I'm going to go through the agentic version. So, but first, let's see how this AI service in our monitoring system receives the captured JFR events. So we use the Java agent to start the JFR recording, and the captured JFR events are posted to an endpoint. And on the monitoring service side, we have a class called JFR event service, for instance, that just fetches all the sent JFR events from that endpoint. And then it's basically saves into a database. And we have the AI service that reads the most recent JFR events from the database. And this is triggered regularly. So this is a scheduled task. And this is how our AI service receives the JFR events. And to implement our AI service, we will be using one of the popular choices, LangChain for J. So let's try to divide our problem and think through it. And imagine we have a small team of engineers that tries to make sense of the JFR data and tries to find if something is going wrong or not. So let's say we have a yellow engineer that receives the raw JFR data. And all it has to do is looking at this data and interpret it and write a summary about it, about the data. And while doing this, it has an access to a documentation that has some description of all the JFR events and their descriptions of their fields and units. So these are really important information. And by using this context, it can generate the processed version of our raw JFR data. And then it can send it to another engineer, which is blue engineer. And blue engineer's task could be looking at the processed data and try to figure out whether there is something going wrong or everything is okay. And if it requires further data to be sure that something is wrong or not, then it can ask for more data from yellow engineer, and they can work together within a loop. So we can create a loop workflow between these two engineers. And once our blue engineer has some findings, it can send it to another engineer, green engineer, and this engineer has an access and control over our microservices. So based on the findings of blue engineer, green engineer can come up with some kind of action plan and decide to take this action to change some things in runtime on our microservices. And if we go one step back and look at the loop workflow and the green engineer, we see a sequential workflow here. So these engineers can be AI agents, and the yellow can be the JFR data processor, blue can be anomaly detector, and green is our self-healer agent. So now we're gonna implement these with LangChain4j's agentic module. Before going into that, implementing all the agents are pretty similar. So I'm gonna go through creating the system prompt for all of them, and I'm gonna refer to some interesting details in each agent. So we're gonna implement the system prompt on a very structured way. So all we need to do is a role, provide a role to the agent. So in this case, for instance, we say that you are just JFR data processor. And if we want our agent to have some access to some tools, then we can define them here as well. And data processor agent has access to two tools that we define. These are read JFR documentation and fetch older events. And we're going to give some context. And in this case, we say that all you need to do is transform this raw JFR events into some structured context. And we finalize with an output format. And this is a format that we define with some fields that we ask from the agents. And here, let's talk about tool or function calling. So it basically enables structured function invocation by the LLM. And all we need to do is to annotate the methods that we want LLM to use with tool annotation. And as we have already in the example, an agent can have access to several tools, and it selects the suitable one at that time and fills up the arguments and calls that method. And eventually, the tool result is fed back to the agent's model to continue or finalize the response. So here, for our JFR data processor agents, we create a class that contains our tool, JFR data processor tools. So the first tool is the read JFR documentation. And with the tool annotation, we mention what kind of tool this is and when to use it. And within the method, there's nothing fancy. We just load the documents and return its content to the agents. And how does the agent use this? So for instance, when it receives something like JDK object allocation sample in the raw JFR data, it can refer to the documents and collect some information. And by using this context, it can create some meaningful, interpreted, processed summaries. And the next tool is fetch older events. Again, it's the same structure. And the thing is, for instance, whatever this method returns is fed back to the agent, and then it just processes it and then gives it to the next agent, and the next agent is anomaly detector. So again, we are seeing a system prompt. We follow the same structure. We give the role, context. This agent is not going to have any tool. This is how we want. And the output formats. And here the interesting thing is, in the context, we provide a short guideline to the agent. We ask for a level of confidence with its findings. So we don't want this agent to come up with a come up with an anomaly detected decision based on just a spike in the heap usage. So we want this agent to build some confidence, and we want it to give us a confidence score. And from here, we can look at structured output. So this is the output format for this particular agent, anomaly detector, that we ask it from. And all we need to do is defining some fields And in this case, we are using LangChain for J's structured output package for the description annotation. And this annotation is just to tell the model that's what each field represents. And for anomaly detector, we are first asking for a reasoning, and then a service name, some key metrics maybe, some trend analysis, whether anomaly detected or not, level of confidence, and whether it requires more data or not. And there's an important reason why we designed it this way. We explicitly guide the model to reason before giving the final answer. Because LLMs generate text sequentially from left to right based on previous tokens. So if we ask the answer first, then the model is gonna commit to that answer without walking through the problem fully. But if it reasons first, all these intermediate steps are gonna change the probability distribution of the coming tokens, which makes the correct answer more likely. So with this structure, we are not only improving the explainability, we actually improve the performance. And finally, our self-healer agent. Again, we see a system prompt, role, tool, context, output formats. But here, the interesting detail is this agent has no idea what kind of actions are available in what microservices. So that's why we're going to receive them via JMX. And we're going to just inject them into this system prompts. So let's open a parenthesis here and revisit JMX. You remember this? We already start creating our operations and attributes. So now we're going to attach some metadata. To do that, we're going to override a method called getMbeanInfo for both operations and attributes. And by using JMX API descriptor, we can create a field. So for instance, we create action field that contains the name of the action. And another thing that we want to do is a field called confirmation. So it's just true or false. And we want to use this, for instance, if the action is a critical action, then we can set this field as true to show that this action should be confirmed by a human before its execution. And to attach all the metadata for operations, we are using mbean operation info. And within this, we give the name of the operation, text description for this operation. This is important because we're going to give this directly to LLM. And if it has parameters or if it returns something, they go here as well. And there's something called mbean operation info.action that indicates that this operation modifies the mbean's state, but it doesn't return anything. There are other types you can check in the documentation. And finally, we're going to return this object. But for attribute, it is very similar, but we are just using mbean attribute info. Again, we have the name of the attribute, type of the attribute, text description of the attribute, whether it is writable or not, and finally we return the mbean info object. Again, we remember here, so this was the part how we discovered the mbeans, and we filtered them out with the ones with type self-healing. So from here, we're just going to call the method that we just overrode, which is getMbeanInfo. And this way, we have access to all the metadata that we attached to the operations and attributes. And finally, when we receive them on the monitoring service side, we just can inject them into the system prompt. And now the self-healer agent has knowledge of what kind of actions are available for which microservices. Okay, now we're gonna talk about how we use LangChain4j to combine everything. LangChain4j's document mentions some components as low-level components. These are like chat model, chat message, chat memory. And if we want to combine them ourselves, it might require an extra attention. But while building our agents, we're going to use the agentic module of LangChain4j, and it acts like an abstraction layer. So we don't have to think about how we're going to orchestrate each components. And this way, it becomes pretty convenient to integrate tools and also provide memory for each agent. So again, we have 3 agents and their implementations are pretty similar. There are some differences that we're gonna go through. But let's first create a template and then see them one by one. So first, we need a chat model. And selecting the model is always tricky. There might be some other parameters that help you decide which vendor, which model to use. And in our case, we decided to use Anthropic's Haiku 4.5 because it is fast. It is good with tool calling. And we're going to use the same model for all the agents. So we can have just one chat model. And by using this Anthropic chat model API from LangChain4j, we give the API key, the name of the model. And here we can also change the model parameters like temperature. If we want some like more creative answers, we can set this value a bit lower. If we want more deterministic, then vice versa. And once we have the chat model, the second thing we need is the interface for each agent. And we use the agent annotation, and we give a user message here and a method. And this method has, in our case, 2 arguments. One of them is memory ID annotated service name. And the reason why we do this, all the microservices are running on separate JVMs, so we would like to analyze them separately. So the agents are going to have separate memories for each microservice. And the next argument is context, and we use the annotation V. I believe it stands for variable from LangChain4j again, and it just becomes a prompt template variable. So whatever we put this in this context, its value is going to be injected into the user message prompt. So then we are using the instance of this interface, and we are assigning the agentic services agent builder. We pass the interface name in this builder, and we provide the chat model. Here we can create the chat memory with just one line, and let's say use the last 10 messages. And this is important for our agents because we are asking for some trends to see what happened in a few minutes or so. And we provide the system message, system prompt, and we give the class that contains the tools in the tools. And this way we build our agent instance. So once we have this instance for each agent, then we're gonna build the workflows. And here, these are the interfaces we created for our agents. The structure looks very similar. And if you see, the context is going to be injected into the user message. So now let's look at the agent builder part. We have the agents, and we define the interface for them. So all the agents, data processor, anomaly detector, self-healer, they have a type. And we assigned them to agentic services agent builder. We provide the chat model. We provide a chat memory. We give the system prompt for all of them. We provide a class that contains all the tools. Anomaly detector doesn't have any tool in this case. And this completes our agents. So now we need to ask a question. How does the data processor knows that anomaly detector asks for more data or not? So it doesn't know directly, but to do that, we're going to use a concept called agentic scope in LangChain4j. And to be able to use it, we are using this output key with just by naming the output of this agent, let's say detection, to make this output shareable among all the other agents in the system. So this becomes a shared variable. An agentic scope is a shared context where agents store and read data to collaborate using shared variables that one agent writes to publish results and the other agent reads it to perform its tasks. So this is a definition from the documentation. And with this output key, we store this agent's output in a shared variable called detection, which is accessible by the other agents. But we're not going to use directly from the data processor side. We're going to use in the loop workflow. So let's build our loop workflow. So we are using the loop builder. We create our detection loop agents. We provide a name. We can set maximum iterations, let's say 5. And here it comes, the agentic scope. So this loop can go forever, but we are going to provide a statement, and we're going to use the scope for that. So we read the state of the shared variable. So if it is null, we are not going out. And then here, the detection was the same output format of whatever we get from the anomaly detector. So we read the more data required flag, and we also check the confidence level. So if this statement is satisfied, then we're gonna exit the loop. So this is, and then we provide the sub-agents. These are the data processor and the anomaly detector, and this is how we build our detection loop. And this detection loop itself doesn't have a type. We haven't created any interface for that. And in LangChain4j, we have this untyped agent. It's like a generic agent. So its type is untyped agent. And we put this detection loop in the sequential workflow. It's pretty similar, but we are using sequence builder. Name of the sequence workflow. We give the sub-agents detection loop and the self-healer. And we now have the decision sequence. And this untyped agent has a method called invoke. So we can just provide our very first input, which is the name of the service and the raw JFR data in the map format to our decision sequence agents, basically. And we get the results. So this is just to summarize all the agents. I don't know how complicated it looked like. I try to make it simplified. So we have the context for all agents. We have the available tools and the output format that we designed for all of them. So now actually we have everything. We remember this diagram. Let's complete this diagram. So our AI service receives the available actions from the MBean discovery, and then it builds the prompt for self-healer agents. And here the agents work together and they come up with a decision. Let's say they come up with a decision enable batch. And then AI service invokes this remotely, and by using JMX clients, we are using the set attributes method that we overrode before. And now we enabled batch successfully in the remote microservice. And this actually completes our monitoring service. And now I want to show some results, like some logs that I got, and just to visualize how the answers might look like from each agent. And it looks exactly how we ask for, of course. So for JFR data processor, for instance, we get the service name. It provides a summary, event types. We ask for some evidence. It also provides that, and the processed metrics. And for anomaly detector, we said we want the reasoning first, and then the service name, some key metrics, trend analysis, anomaly detected, false in this case, confidence level with 72%, and it asks for more data. And for self-healer, we ask for reasoning again, because it's gonna come up with an decision of which action to take, so it's good to ask the reasoning. And some trend analysis. Action is none in this case, and it also has a confidence level. And now, let's see how the end result looks like. So on top, you see the logs from order service, and at the bottom, you see logs from monitoring service. So we are just receiving orders in the order service side, and we are fetching them in single mode. And in the meantime, on the monitoring service side, we have the anomaly detector, doesn't detect anything, the confidence level, and it doesn't require more data. But suddenly, we received tons of orders synthetically, and our data processor keeps processing the data, of course. And anomaly detector started detecting some anomaly with confidence level of 72%, and it requires more data. And in that case, data processor agent calls its tool fetch older events. And again, it processes them and send it to the anomaly detector. And this time, anomaly detector tells us that an anomaly is detected with a higher level of confidence, 90%, and it doesn't require further data. And now it's self-healer's turn. And based on the result from anomaly detector, self-healer decides that let's enable the batch. And for enable batch, we said that it's not that critical, so we can just execute it. But in production, if it's a critical action, then it might be good to bring the human in the loop, and the human can reject or accept the suggested action. And its tool called process decision self-healer calls this tool. And this is the place, for instance, we can put this confirmation thing by the human. And we enable the batch remotely. So we see on the order service side, it is set successfully. And from now on the order service side, we are fetching the products as batches in batch mode. Perfect. So this is the overall picture of what we have done today. So we have the microservices, we use the Java agents to start the recording, and we stream the JFR events to the monitoring service. We use agents, and then we use JMX to change things on microservices in runtime. So, and finally, the dashboard looks nice. It is green. Green is a good color if you're a programmer. And that's it for today. Thank you so much for listening.